So this will be the first part in a mechanism for intelligence. And in this part, we'll discuss the beginnings. We'll discuss how to find initial direction and meaning from nothing. So let's get started. To make things concrete, let's solve a specific problem. And let's first look at what we, the problem solvers, are given. So for each instance of the problem, we can perform any number of steps. At the beginning of each step, we'll receive one observation, which will be some floating point value. Then, we can either halt, ending our interaction with this problem instance, or we can perform a combination of two actions, outputting a continuous floating point value, and choosing from one of three discrete options. Then we'll move on to the next step. After we halt, we'll get a score, which will either be 0, which is bad, or it will be 1, which is good. And this is it. This is all we're given initially to try to solve this problem. From this limited starting point, we'll need to somehow figure out what the score means, what these actions do, how these observations can be used, and ultimately, how to consistently get the highest score we possibly can on this problem. But, to help make things more instructive for the audience, let's peel back the curtain to look at the underlying details of this problem. The problem solver, of course, is never given any of this. So this is actually a classic computer science problem, sorting, but on tape. Each problem instance occurs on a tape of data 2 to 10 squares long, initially filled with integer values randomly from 1 to 10. And there's a tape head, which is how we'll interact with the tape, initially pointing to the leftmost square, which I'll also be referring to as the first square. At each step, we'll receive the value of the square currently pointed to by the tape head, which is our one observation mentioned earlier. For example, if the tape is currently 6, 4, 10, 5, 3, and the tape head is pointing at the first square, then for this step, we'll receive an observation of 6, the value of the first square. Then, we can either halt or perform two actions, adding a value to the square currently pointed to by the tape head, which is the floating point output mentioned earlier, then moving the tape head left, moving the tape head right, or keeping it in place, which are the three discrete options mentioned earlier. For example, if we perform 1.5 right on the current tape, then we'll add 1.5 to the first square, where the tape head is currently pointing at, then we'll move the tape head right, so our next step will begin with the tape head on the second square. One detail to add here is that the tape head is moved beyond the boundaries of the tape. There are extra warning squares at the ends, which cannot be moved past, which will return a value of -100 when read. Finally, the scores of 0 and 1 mentioned earlier correspond to whether the final tape after halting is correctly sorted or not. We receive a 1 if it is correctly sorted, and a 0 if it's not. Here, the sort doesn't have to be completely precise. As long as all the values are within 0.1 of what they're supposed to be, it counts as correct. In our current example, this final array of 3.1, 4, 4.95, 6.02, 10 has values which are all within 0.1 of the correct sort, 3, 4, 5, 6, 10. So this results in a score of 1. So in the following, we'll see how the sorting problem can be solved. Here in part 1, we'll see how we can overcome the initial lack of knowledge to build out an initial partial solution. In the following part 2, we'll see how to add increasing sophistication until we finally arrive at a sorting algorithm that many might recognize. So let's get started. So the first step in the mechanism is what I'll call exploration. And this step should be fairly intuitive. Initially, we don't really know anything. So there isn't much else we can do besides randomly trying different action sequences and seeing what happens. For example, let's try this 0.2 left minus 0.4 right sequence on a random problem instance, which happens to be 10, 3, 5, 3, 6. Though this underlying tape is not something the problem solver sees, of course. And we get back some observations, which we won't initially know how to use, so we won't worry about these for now. The problem solver again doesn't know this, but all this action sequence effectively does is to add 0.2 to the first square, which clearly doesn't lead to a correct sort. So we get a final result of 0. Okay, let's keep trying. Next, let's randomly try the 0.9 stay sequence on another random problem instance, which also doesn't lead to a correct sort, so we get 0 yet again. And so we'll keep trying random sequences on random problem instances thousands, millions of times, and hopefully, occasionally, we'll get lucky and randomly try, for example, this -1 right plus 1 stay sequence, which swaps the first two squares by 1 on this 2, 1, 7 problem instance. This is a sequence that can lead to correct sorts, and luckily, this problem instance is one in which it does. And so we get a score of 1. So then what we'll do is that we'll save the action sequences that happen to have resulted in higher scores to use in the following steps, where we'll see if we can build upon them further. By the way, the reason why we have to keep using new, different problem instances is because we cannot ever fully capture a problem instance to reuse. This is because we only see the underlying world of an instance through our observations, which, as we just saw, often only offer a limited view. In addition, we only see a problem instance as it reacts to the single action sequence we try on it. We don't know how it might have behaved differently had we tried a different sequence on it. So because we only see an instance partially and on only one timeline of actions, we can never know the entirety of the instance, so we cannot capture it. Now, since this particular sorting problem is an artificial one that is easy to simulate, getting new problem instances is easy. But it is the case that for many real-world problems, it can be costly to find and experiment on new instances. In these cases, it can be beneficial to use world modeling, where we first develop an understanding of how the world works, then use that understanding to generate artificial problem instances to use, which is something we'll touch on more in the wrap-up. Before discussing the next step though, to help understand why it's needed, now is a good time to talk about existing work and where it falls short. The type of general problem solving tackled here is probably most closely related to the field of reinforcement learning, which has achieved some notable results. Most significantly, the reinforcement learning AI AlphaGo was the first AI to achieve superhuman performance in the game of Go. And reinforcement learning has also been used in autonomous driving, video games, and so on. Generally speaking, reinforcement learning tries to model and solve problems as Markov decision processes. If modeled effectively, this will enable us to solve each step of the problem independently from any other, and also enable us to solve each step in an identical way, vastly reducing the problem-solving difficulty. Specifically, once solved, we'll use the same calculations again and again on each step to select what actions to perform, based only on each step's current observations and state. State here is a concept key to Markov decision processes enabling this to work. So even though we want to treat steps completely independently, knowing past history, so what happened in previous steps, can be necessary for selecting actions optimally. So information on past history is needed. But building a growing record of history and processing all of it every step is not practically feasible. So instead, we'll compress history down into a small constant amount of data known as state, which will repeatedly update in each step and pass on to the next. How well we compress history into state determines how effective our modeling is. And in fact, for reinforcement learning to achieve good results, the modeling has to have a quality known as the Markov property, which is that the current observations and state need to always contain all the information necessary for ideal decisions to be made. There cannot be past history that would have mattered but we forgot because it wasn't included in our state. Now, the Markov property can always be attained with ideally constructed state, but unfortunately, this is difficult to learn. For an AI to learn how to construct ideal state, it needs to learn what parts of history to value and what parts to discard. But as we'll see soon, this will need the AI to not treat steps independently of each other, breaking the main reason to use Markov decision processes and state in the first place. So instead, the state is often human constructed using expert knowledge, where humans identify what is important in past history, and humans then figure out how to abstract that into a small constant set of inputs to give to the AI. This not only takes significant effort from humans, but the AI also becomes limited, at least partially, by existing human knowledge. As a result, reinforcement learning, through its reliance on Markov decision processes, is not an effective tool for universal problem solving. But let's look at this limitation more closely. What exactly happens if we try to learn state while treating steps independently? Specifically, let's look at our sorting problem. But let's not even think about fully solving sorting, but instead just focus on the simple sequence -1 right plus 1 stay. This sequence solves problem instances where the first two squares are off by 1, so it can be a good sequence to learn, especially early on. But can it be learned by reinforcement learning? So we need to independently learn to perform -1 right on the first step and +1 stay on the second. So let's start by looking at the second step. Here, the problem is that in general, +1 stay is a bad action. Even though it can succeed when -1 right is a starting action, for most other starting actions, it cannot ever succeed. Now, this would be okay if we only perform +1 stay in the specific circumstances in which it's good. But our observations here cannot help us identify these circumstances. In fact, the only way for us to learn to value and perform +1 stay is if we've already memorized whether or not -1 right was the previous action, so that we'll be able to perform +1 stay only when -1 right was a previous action, where it does have a good chance of succeeding. But let's now look at the first step. The problem here is that, in general, -1 right is also a bad action, and there's also little value in memorizing whether we performed it. Even though -1 right can succeed if +1 stay is the follow-up, for most other follow-ups, it cannot ever succeed. And similarly, even though memorizing whether or not -1 right was performed can be useful if +1 stay is the follow-up, again, for most other follow-ups, memorizing whether -1 right was performed will not be valuable. So ultimately, because they each depend on the other, we'll neither learn to memorize -1 right nor learn to value +1 stay. And as a result, we'll be unable to learn this -1 right +1 stay sequence. And in general, when we treat steps independently, we'll miss many important synergies between steps like this, so there will be many sequences that we won't be able to properly value and learn. Specifically, unless a sequence can be built up from actions that are independently valuable, then it won't be learnable. Instead, for this sorting problem, what reinforcement learning might end up learning, for example, is to start off with 0 left, an individually valuable action. 0 left makes no changes to the tape, so pre-sorted problem instances remain correctly sorted, then the tape head moves off the tape, so different follow-up actions that might otherwise ruin the sorted result have no effect instead. So 0 left leads to relatively high scores in general. But obviously, this traps us in a local maxima of only being able to solve problem instances that are pre-sorted. Now, continuing with our new mechanism. So obviously, we need a different approach. Instead of reasoning about steps independently, we have to reason about entire sequences in their totality. But there's a big reason why previous approaches, such as reinforcement learning, avoid this. Reasoning on full sequences leads to a combinatorial explosion of possibilities. Not only are there infinitely different sequences of infinitely different lengths, each of which may have a unique interaction with the problem, but to handle a wide variety of problem instances, solutions need to be a combination of sequences, and there are infinitely many unique combinations on top of everything else to consider. So in the following, we need to somehow progress through this combinatorial explosion. And we'll look at one way of doing this, which I'll call checkpointing. So obviously, it's simply not feasible to just naively explore all possibilities. And instead, we have to be smart about where to spend our effort. From our previous step exploration, we captured some sequences that resulted in high score when we tried them. Let's start by evaluating these further. While these sequences happen to score well the one time we've tried them so far, we'll want to know how they do in general, so we're going to further try them on a large number of problem instances. For example, for this -1 right +1 stay sequence we found from exploration, we're going to try it exactly as is, again and again, on random new problem instances. And as we're doing so, we're going to measure two things. First, we're going to measure the average score to know if the sequence is good in general, or if it just got particularly lucky the first time we tried it. Second, we're going to measure how much information the sequence gets. And this, I'm going to explain in a bit more detail. So let's compare two sequences, 0 left and 0 right. These two sequences actually solve the exact same problem instances that are pre-sorted, so they have the same average score. However, while executing, 0 right sees a second square from the tape, which will let it better predict what the final score will be before it actually halts. For example, if the first two squares are 2 and 3, then 0 right can know that it will have a great chance of succeeding, because the first two values are sorted and small. And if the first two squares are 2 and 1, then it can know that it's already guaranteed to fail, because the first two squares are already not pre-sorted. Specifically, as we try a sequence on a large number of problem instances, we'll learn what the average scores are given the observation seen. This is a supervised learning problem, and we'll leave the details to part 3, but for now, we'll simply assume we can do this perfectly. So when ZeroRight, for example, sees 2 and 3, it will have learned to expect an average score of around 0.29, which is the probability that a problem instance starting with 2, 3 is fully pre-sorted. And on the other hand, when it sees 2 and 1, it will have learned to expect an average score of 0. Compare this with 0 left. Because 0 left doesn't see the second square, the average scores it learns will be less accurate than 0 rights. It will, for example, expect an average score of around 0.18, both when the instance starts with 2, 3, as well as when it starts with 2, 1. Information is a measure that captures this difference between 0 left and 0 right. The higher the information, the better a sequence's observations will be at predicting the final score. Specifically, information is equal to the difference between the predicted average scores and the actual scores, averaged across all problem instances, or practically, just across a large number of instances. But why would information be something we want to care about? Simply speaking, information will enable us to make decisions. For example, if we're solving a problem instance with 0 right, and we see 2 and 3, we know this is a situation where 0 right will likely get a good score, so we can proceed with confidence and halt as usual. But if we instead see 2 and 1, we know that this is a situation where if we go ahead and halt, 0 right is guaranteed to fail. So instead, maybe this is a spot where we should try something else. So now, we can finally talk about checkpoints. Checkpoints are spots in relatively high scoring sequences that have relatively high information. For example, for the sequence 0 right, the point right before halting is a good checkpoint. This sequence successfully solves pre-sorted problem instances, so it is relatively high scoring compared to other early sequences. And as just discussed, 0 right lets us see a second square of the tape here, giving this spot a particularly high amount of information. Checkpoints will be spots that we'll want to continuously revisit as we build our solution. As we'll see soon, they'll let us reuse good sequences we've already found, while also enabling us to find synergistic alternatives. But checkpoints don't need to just be at the end of sequences. For example, let's look at this -1 right plus 1 stay sequence. Because the second action is stay, our third observation will be from the same square as our second observation. And in fact, our third observation will just be the second observation plus 1. This means that the first two observations alone already give us as much information as if we had all three observations. So instead of checkpointing at the end, we can instead checkpoint immediately after -1 right. By checkpointing earlier, we can begin adjusting our actions sooner, enabling a faster reaction to the observations we receive. So in addition to measuring information for the entire sequence, we'll also measure the information for all the prefix subsequences. Then, we'll select the best checkpoints using some heuristic based on average score, information, and how early they are in the sequence, and use the selected checkpoints in the following. So let's revisit exploration again. But this time, instead of trying random action sequences from scratch, let's try random sequences starting from the checkpoints we just found. So for example, for this checkpoint we were just looking at, we're going to repeatedly reuse the same subsequence from before the checkpoint, -1 right, and try random sequences from it. For example, starting from -1 right, let's randomly follow with -1.4 stay and see what result we get. Then, starting again with -1 right, let's try following up with +1.7 right plus 8.8 left. And like previously, we'll repeat this many times. And hopefully, occasionally, we'll find sequences like +2.1 left minus 0.9 stay that result in relatively higher scores, which we'll save and use in the following. And let's also revisit checkpointing again. And like previously, we'll try the potential sequences on a large number of problem instances and measure their average score and information. For example, for this -1 right plus 2.1 left minus 0.9 stay sequence we just found, we'll try it again and again on random new problem instances, just like earlier. But now, we can combine sequences to begin building bigger, more effective solutions. For example, let's combine our original sequence from which we found our checkpoint, -1 write, +1 stay, with a new sequence we just found. And this is where we will really benefit from the idea of checkpoints. Because these two sequences share the same checkpoint, they can easily be combined into a bigger solution, where we'll start with a subsequence they share, then at the checkpoint, flexibly choose between the two options depending on which is more likely to achieve better results. The only question then is, for a particular problem instance, how do we choose which branch to take? Remember that for each sequence, as part of measuring information, we learned what average scores to expect given what observations we're seeing. So all we need to do to choose between branches is to compare their predicted average scores and choose the branch with the highest. For example, here, the top branch swaps the first two squares by 1, while the bottom branch swaps the first two squares by 2. So if we see 3 and 1, we know that the top branch cannot ever succeed, but this is a promising start for our bottom branch. So our bottom branch is what we'll choose to perform here. But if we see 3 and 2, we know that instead, it's the top branch that is likely to get a good score here. So the top branch is what we'll choose instead. High information was important here because it makes it more likely that we'll be able to make good decisions at the checkpoint. The higher the information, the more likely that we'll be able to tell when sequences are good versus when they're not, better enabling us to use sequences when they're strong, hide them when they're weak, to create solutions that are sharper and more robust. And by the way, if there are more than two branches at a checkpoint, to choose between them, we simply have to compare the learned score of every branch and choose the branch that has the highest score. And just like previously, we'll look for good checkpoints from where to build out our solution even further. For example, this bottom sequence, -1 write, 0 write, plus 0.9 stay, goes right yet again after the checkpoint to see another square of the tape to get yet even more information. So this can be a good spot for a new checkpoint. And so, we'll keep on repeating these two steps of exploring and checkpointing to gradually build out a bigger and bigger solution. We'll use deeper and deeper checkpoints to explore for longer and longer sequences to add into our solution. Then, we'll look for new checkpoints on these new sequences from which to explore even deeper. And as long as we have effort to spend, we'll repeat these two steps indefinitely to continue improving our solution further and further. One detail to mention is that as our solution is extended and improved, we will want to correspondingly update our learnings on the average scores given the observation seen. For example, let's say initially we are choosing between these two branches, where the top branch swaps the first two squares by 1, while the bottom branch swaps the first and third square by 1. So for the observations 3 and 2, we'll want to choose the top branch, but for 3 and 3, we'll want to choose the bottom branch. But if we extend the bottom branch to where it can both swap the first two squares by 1 and swap the first and third square by 1, depending on which is better, then for both 3 and 2 and 3 and 3, we'll want to choose the bottom branch. So we'll need to update our learnings to adjust for this. To do so, we'll need to try the entire bottom branch with its branches and learnings included on more problem instances, and update the bottom branch's predicted scores given the observation seen. But here, another detail to mention is that as we keep trying to improve our solution, we shouldn't focus solely on the same high-scoring branches, but we should occasionally also try other less explored checkpoints. For example, if our bottom branch started out with high-score information, and we've been focused on extending it, it might be that it actually leads only to a local maxima. So to prevent getting trapped, we'll want to balance by occasionally exploring from checkpoints we haven't visited as much. These might not initially have as high score or information, but it might be that ultimately, a better solution can be found through them. The thing to keep in mind is that exploring and checkpointing is a heuristic. We are trying to avoid the combinatorial explosion of trying every combination of combinations, by instead building up solutions incrementally, focusing on sequences that are effective and synergize well. But because this is a heuristic, there's no guarantee that this will lead us directly to the best solution. And instead, we'll want to balance exploiting the checkpoints that initially look promising with occasionally exploring even the less appealing checkpoints, so that ultimately, we will always be able to work our way out of local maximas and progress towards the best solution. And this can be done, for example, using an algorithm like Monte Carlo tree search. So anyways, we'll continue to explore and checkpoint to build up bigger and better solutions. And this will be the end of part 1. However, this doesn't come close to fully solving sorting yet. There are too many possible problem instances for us to solve them all using a tree of branches. This doesn't seem to capture ideas we humans associate with sorting, like comparing and swapping, and this doesn't match up to the sorting algorithms effectively used by humans. So in the next part, we'll see how we can build upon exploring and checkpointing to add increasing sophistication, construct additional structure, until we're finally able to fully solve this sorting problem.